shouldn't care about anything except making money. No ethics, no social responsibility, just profits. And people actually agreed with this. Yep, that's Friedman's doctrine. The idea that a company's only responsibility is with shareholders. If it's legal and it makes money, it's good business.
Ah, yes, because historically businesses have always made great moral decisions.
Okay, can you try again at exactly 12 p.m. because the attendance QR now is quite sensitive. I'm not so sure, but just try it. Okay, can you try now? Boleh tak?
Doctor, the QR code is not valid.
Masih tak boleh ya?
Oh, masih tak boleh, Doctor.
Lama. Saya try generate semula. Sorry. Not. All right.
Doctor, but the session 3 time is wrong. You put at 8 a.m.
But I changed already. Never mind. Just scan it. Is it? 8 a.m. Never mind. Ah. Oh, you have to sign it again. Sorry. For section 3. Okay, I think we left this QR code. So for the Muslim, we start with the Umul Kitab Al-Fatihah. Okay, we continue with our syllabus. So last week we stopped at here, where we trying to use the angle and magnitude criteria to test whether at any point that point is part of the closed loop or the root locus of the system or not. Okay, so if it is fulfilling the magnitude and angle criteria, so means that that point is part of the closed loop poles, right? So we have stopped here. So for those who missed this class, you can check at the e-learning where I did put the recorded videos, so you can watch it again. Okay, so we continue with the real topics for this chapter, which is we're going to doing the sketch of the root locus. Okay, so the sketching is divided into two parts. Okay. Okay. It has two parts in the root locus. One is the sketching part. Okay, sketching. And the other part is the refining. Sorry. Okay. In sketching, we have 5 rules need to be followed. Okay. And for the refining, we have another 4 rules. Okay, rule number 6 to rule number 9. Okay. So we start on the sketching the root locus. Let's we consider this closed loop block diagram or the feedback block diagram. So we have the forward transfer function as kg and the feedback as hs, right? And the transfer function is generally can be written like that, where the numerator part we have the gain k and also list of the poles. Okay, so s plus the 0, s plus the 0 number 1 up to s plus 0 number m. Okay, so the numerator is for zeros and denominator is for the poles. Okay, so for the denominator, we have s plus pole number 1, s plus pole number 2, up to s plus pole number n. So the rules of catching the root locus, we should make sure that the number of zeros should be equal or less than the number of poles. Okay, it cannot be zeros is greater than poles number. Okay, it at least should be exactly same number. Okay, for example, we have 3 zeros and we have 3 poles. Okay, this one okay. We have 3 0 and we have 5 poles. This one okay. We have 3 0 and we have 2 poles, and this is not possible. Okay, so should minimum the number of zeros should be equal to the number of poles. Okay, we as I mentioned just now, we have two parts. One is for sketching, and the other one is to refine the sketch that we have drawn. Okay. So we start on the first three rules. Okay. So the rule number one, saying that the number of branches are equal to the number of closed loop poles. Okay. For example, we have the transfer function is given by, okay, the forward transfer function is given by k s plus 2 s plus 3 s plus 4 s plus 4. Okay, so we know that the number of poles is equal to 3. Okay, and basically this is for open loop transfer function. If you convert it into the closed loop transfer function, okay, we should use kg divided by 1 plus kgh formula. Okay. Is this formula, and basically we're going to have another closed loop transfer function. Okay, blah 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 s to the power of 3, and for example it is finally 2k. Okay, so we have also the order of 3 for the closed loop transfer function. Following the number of pole for the open loop, we have 3 poles, and the closed loop also is going to be 3 pole as well, because the order going to be the same order, which is s to the power of 3. So basically, as mentioned here, it is the number of branches is equal to the number of closed loop poles, and it's also equal to the number of open loop poles. Okay. So meaning what? Later we see a few examples. The second rule saying that the root locus is symmetrical about the real axis. So meaning that if we have an axis like this, the S-plane, so the root locus should symmetry. For example, previously we have seen one root locus that is look like this. We have two poles, started from two poles, open loop poles, and finally it goes like this, and the other one is goes like this. Okay, so we have, in this case, we have two branches, because the order of the system is s to the power of 2. You can refer back to the previous example. And the root locus, as we can see here, the upper part and the bottom part is symmetry about this real axis. Okay, so that is mentioned by rule number 2. The rule number 3 is saying that on the real axis, okay, for k is greater than 0, the root locus should exist to the left of an odd number of the real axis of the finite open loop poles and or 0. Okay, let's see the example here. For example, for rule 1 and 2, we still considering the previous example, okay, where we have found that the root locus is going to be like this. Okay, so rule number 1 saying that the number of branches is equal to the number of closed loop poles, or the number of open loop poles equal to 2. So we have two branches. One is started from here, goes to like this. Okay, and the other one is from this another open loop poles here, and meet at this what we call as the breakaway point. And it breaks to the downward. Okay, so we have one, which is including this one, and the other one is these branches. So this is considered as 2. Okay, the rule number 2 saying that the root locus should be symmetry. So we can see that it is symmetry for the upper part and the downward part. Okay. Two branches are shown originate from origin and -10. Okay, so the root locus should started from the open loop pole. Okay, started at 0 or origin. So origin means 0, and it started at -10. Okay, why is one is goes to the right and the other one is goes to the left? Why the root locus it is goes like that? It's not going to the left here. Anyone can guess? Anyone have any idea? No idea? Okay. So it is actually related to the rule number 3, where it's saying that there will be a segment at the left of an odd number. Okay. So the odd number means that if you look at all the poles that are located on the real axis, so we only considering the poles that are located on the real axis. So we have 2 poles here and this one. Okay, so I draw it again. So we have 2 poles. One is at negative 0, and the other one is at -10. Okay, 2 open loop poles. Okay, it should start from these 2 poles. Okay, and if we count it from the right, okay, so we can count 1, and this is the second one. Okay, so the statement from the rule number 3 saying that there will be a segment. There will be a segment at the left of the odd number. Okay, so in this case, the odd number located from this pole at the origin. So it is from here to another pole here. There's going to be a segment. This segment going to be a part of the root locus. That's why the root locus is going through this segment rather than it goes to this side. Okay, because this side there will be no root locus over here. Okay, so that is means by the rule number 3. Okay, let me look into another a transfer function to represent rule number 3. So in this case, we have 0 at -3 and -4, and poles at -1 and -2. Okay, so if we locate all those 0 and poles on the axis, so we have poles at -1 and -2. So that is the poles here, -1 and -2, and -3 and -4 for the 0. Okay, represented by the circle. Okay, so if we count this, all the poles and 0 on the real axis, we should start from the right. 1, 2, 3, 4. So that means we should consider there will be a segment or a few segments at the left of the odd number. So we have 1 from this odd number. So it goes to the next poles. It doesn't mean it should go to the poles. Sometimes it goes to the 0 here. But this for this case, we have another poles at the left. Okay, and another one, we considering the 0 at number 3 here. So there'll be a segment at this odd number, at the left of odd number. So it is connected to the another 0, okay, at -4. Okay, so this is rule number 3. So later on, the full root locker is going to be like this. One is it is going out from this pole to the right, and from this pole to the left, and it meets, okay, at a breakaway point, and then it break away, and it's trying to find okay, so for this case, it's trying to find where is the 0 located. Okay, it is at the left side here. So it goes to here and it is break in here. So this is what we call as the break in. And then it distributed into the two parts. It goes finally to the 0. Okay, so part by part. So it's comprised of two branches because it has two poles here. Two poles mean just now the first one probably is it goes like this, then go to here and then ended at here. So it's considered as one branch. Okay. Another one, it goes from another pole here to the left, okay, and then it go downside and then meet at the same point here, and then it goes to another 0 here. Okay, this is considered as another branch. Okay. Any questions so far? Okay, good, thanks. All right, so we continue with the next rule, the starting and ending point. Okay, so the root locus begin at the finite and infinite poles of GSHS at k equal to 0 and end at the finite and infinite 0 at gain k approaching infinity. Okay, so there will be a few possibility of the root locus root. One is it started from a pole, okay, and then it ended to a 0. Okay, every time it should be a pair. Okay, pair between pole and 0. Okay, for this case, it is a complete pair because we say that it is finite pole, and this is also finite 0. What does it mean by finite here? So this is only one. Finite pole and finite 0 means that from if you considering back this one, so here all these poles and 0 that exist on the transfer function, we consider it as finite poles and 0. Okay, and the poles or 0 that are not exist on the transfer function, we call it as infinite. Okay, so as I said just now, this is the first possibility. The second possibility could be from the pole and then it goes to the 0 at infinity. So it doesn't have the finite 0 here. So this is infinite. Okay, but the poles here is still finite poles. So that is the possibility. And then it could also be from finite the finite pole to infinite pole. Infinite poles from the infinity to the finite 0. Okay, and we have another combination. I think that's it. Okay, that's the combination. Right. Later we look into example to be more clear on what does it mean here. Okay, so we consider this transfer function. So k over s plus 1, s plus 2. So we have nothing 0. Okay, we have no finite 0. No finite 0. Okay, because we doesn't have anything at the numerator, but we have finite poles here. Okay, where the finite poles are located at 0, -1, and -2. Right? So where are the infinite zeros? Okay, rule number 5 will help us to locate these zeros at infinity. Okay, all these poles still have their own pair, but in this case, all those poles are connected from the infinite. Sorry, it is not like this. Okay. So this pole goes to the finite zeros. This pole also infinite zero. This pole is for there are no finite zero appear here. Okay, so the zero are located at the infinite. Okay, this I have explained just now. We have this root locus. Okay, so once root locus goes like this and ended like this, and the other one goes like this and ended at the 0. Okay, so the poles goes to the 0. The poles goes to the 0, and all those 0 and poles are finite 0 and poles. Okay, the root locus begin at the finite poles, which is -2 and -1 and -2, and ended at the finite 0, which are at the -3 and also -4. Okay, so just now we are confusing on what is infinite 0 and infinite poles. Okay, rule number 5 will help us to identify where are the location of that finite 0 and poles. Okay, so the rule number 5 saying that the root locus will approach straight line as the asymptote line when the root locus approaching infinity. Okay, so basically I'm saying that rule number 5 is to look on the asymptote. Information of the asymptote minus the number of finite zeros. Okay, and the real axis intercept at the real axis intercept at sigma a, okay, where sigma a is given by the summation of finite poles minus summation of finite zeros divided by finite poles minus number of finite asymptote. Similar information there. And the third one is the asymptote angle given by theta A equal to 2k plus 1 times phi, or it also can be written like this, times 180 degrees divided by the number of asymptotes, which is actually equal to this formation. Okay, let's be trying to apply all this formula. Right. So this is just example. Okay. So in here, we start on the rule number 1, 2, 3 up to rule number 5. Okay. So let's say the first rule saying that what the number of branches should following the number of poles. Okay, we have 1, 2, 3, 4 poles. Okay, there should be 4 branches or 4 branches of the root locus. Okay, the number 2 is saying that the root locus is going to be symmetry. Okay, and the third one saying that there will be a segment at the odd number at the left side of the odd number. Okay, we trying to number it 1, 2, 3, 4, and 5. So we choose the odd number. So there will be segment at the left. There will be segment at the left of odd number, and another one here. Okay, we can see that this root already completed because we to the left. The root locus already completed because the pair is already equal pair, meaning that the number of poles equal to number of 0 here, 1 to 1. Okay, so this one is completed. And this one probably completed because it's not going to be return it back to here. It should go to the left to infinity 0. Okay, so from this pole, as there is a segment here, so it goes to the left and it's approaching 0 at infinity. Okay, so this is branch number 1, this is branch number 2, and branch number 3 and 4 are here. Okay, from these 2 poles, one will go to the right because the segment is in between here, and another one goes to the left. Okay, so this is considered as branch number 3. This is branch number 4. One, it meets at the point here. So this point is called as the breakaway point. Okay, it break away. One goes to the upper side. Okay, and it's trying to make a curve until it's crossing at this j omega crossing, and it's exited toward the right side. Okay, supposedly not like this. Okay, it goes like this. And the way this finally root locus will end it following the what we call as this asymptote. So later we will learn how we can draw this asymptote line. Okay, let's extend this asymptote line like this. Okay, so the root locus that we have just now, this root locus, it goes to the right, and then it's trying to follow this asymptote line, and finally it will exactly following the asymptote line. Okay, similar to this one. Let's say I extended this one. So this root locus goes to the right, and then finally trying to reach this asymptote line and following this asymptote line. Okay, so what mentioned by rule number 5. Okay, that's we trying on this example, example number 3. So from here, let's say we try to identify rule number 1 about the branch. So how many branches? How many branches that we have? Okay, 4. It's following the number of poles. 1, 2, 3, 4. So supposedly there will be 4 branches of the root locus. Rule number 2 is saying that symmetry. Okay, let's leave it for a while. Rule number 3, there will be a segment. So if let's say we draw, okay, and we place all those poles and poles and 0, -1, -2, -4, -4, and 1, 0 at -3. Okay, so rule number 3 saying that 1, if we number it, there will be a segment at the left of odd number and at the left of odd number. Okay, I did missing one. Okay. This is not right. This is not right. I did miss one pose here. Another one pose is located at the origin at 0. Okay, so we have 4 poles and 1, 0. Okay, so if you number it, 1, 2, 3, 4, 5. So there will be a segment over here. There will be segment over here. There will be segment over here. Is it the same as just now? Okay, this is actually the same as what has been discussed here. Okay, so that's why just now we have this branch number 1, branch number 2, branch number 3, and branch number 4. So finally, the root locus is going to be make a curve toward the right side, where this curve will be guided by a line, what we call as the asymptote line. Okay. So we stop at rule number 3 is the segment, and rule number 4 is what? Check sometime. Okay, starting and ending point. The starting and ending point, one of it will have a finite 0 pair. Okay, because we have a 1 finite 0 here. So one of it will have its own pair. So this is not to the right. This should be to the left, because it started from poles and ended at 0. It could be like this, or it could be like this. Okay, it's depending on the location of pole and 0. Okay, that is starting and ending point, right? And rule number 5 saying about the, so this is rule number 4. Rule number 5 is for the asymptote. Okay, the first thing is the number of asymptote. Number of asymptote is the number of poles minus the number of 0. So in this case, we have 4 minus 1. So we have 3. Okay, so the asymptote number should be 3. Okay, that is the first information. The second one is where is the location of the asymptote point? The sigma A is equal to the number of finite poles, not the number, the summation of finite poles minus the summation of finite 0 divided by the number of asymptotes. Okay, so in this case, we have the finite pole. What are poles exist on the from the transfer function? Okay, we do have 0 and plus -1 plus -2 plus -4 and minus -3, and divided by the number asymptote is 3. So overall, we do have 3, 7, 3, 4, -4/3, which is -1.33 something. Okay, so this is the sigma A, or the asymptote point. Okay, the third one is the angle theta, given by 2k plus 1, 180 degrees divided by number of asymptote. So we have 2k. Okay. So what is actually k that need to be used here? Okay, k is integer number. Okay, the integer number which is from 0 plus minus 1. So I consider just 1, 2, 3, and so on. So which is k that we need to use? Okay, it's depending on the number of asymptotes. So in this case, we have asymptote is equal to 3. So we're going to choose the first 3 integer, okay, up to 2 only. So we're going to use 0, 1, and 2. Okay, so if let's say taking the theta A number 1, so this is going to be 0 plus 1 divided by time 180 divided by 3, which is 60 degrees. Okay, so if you take the theta A number 2, so we use 1. 1 times 2 plus 1 means 3 time 180, which is 540 divided by 3. Okay, which is 180 degrees. Right? Theta A3 is, if you choose 2, 4, 5, 580. Berapa? 40. divided 3, which is, betul ke? Sekali. Which is 300 degrees. 300 degrees. Okay. Again, jadi berapa? 5 kali 8, 40, 900. Bagi 3. Oh, it's 900. 900 divided by 3, which is 300. So we have 3 angles here. 60 degrees, 180 degrees, and 300 degrees. Okay. So just now we identified that the asymptote point located at -4/3 or equal to -1.33, which is somewhere over here. Here is -1.33. Okay, so this is the starting point of the asymptote. Okay, all those asymptotes which it should start from this point. And we have 3 angles, theta, which is 60, 180, and 300. Okay, so if we consider this reference point, so 60 degrees is started from here to here. So this is 60 degrees. 180 degrees from here to here. 180 degrees, and 300 degrees is basically -60, or you can take the full one. Is here. Okay, this is for 300 degrees. Okay, then we draw the line. This is the asymptote line for this angle, 60-degree angle. We draw the line for 300 angle. So this is asymptote number 2. And the third asymptote is just 180 degrees. So the asymptote is like this. Okay. So meaning that the root locus should lie on this asymptote line. Okay. As we can see here, just now we have settled with this one. This poles will go to this 0 completely. Okay. And this poles here, just now we unsure where it is should go. Of course, we know that there will be a segment here, but is it will go straight to the left, or somehow it going back, returning back, make a U-turn. So, but for this case, it's not going like that. So it should go straightway to the left because it is following this asymptote line just now. It is 180 degrees. Okay, so from here it goes to the left, to the infinity point, infinity 0. Okay, and then for the other 2 branches here, okay, as I mentioned just now, when it break away from this point, it trying to go, it will not crossing like this. It will not go like this or like this because it is breaking the rules. Okay, it will not crossing this asymptote. It should finally following this asymptote line. Okay, and later on we're going to verify one more thing, the j omega crossing point here, whether it exists or not. Okay, because the j omega crossing point exists, so that's why it should crossing these 2 points. Okay, so the branches should making a curve, okay, crossing the j omega point here, and finally it will following this asymptote line to the infinity. And the other one also same, goes like this and crossing the j omega point, and finally is following the asymptote line at the infinity. It's trying to find the 0 at infinity, but the 0 is actually we call it as an infinite zero. Okay, also similar to this infinite zero. This is finite zero, but here also infinite zero. Okay, so far, any question? Do you understand? Okay, thank you. So let we look into another example here. All right, good, thanks. Okay, these are quite similar examples. Sketch the root locus for unity feedback system that has the Ford transfer function. So we need to go through all the rules from rules number 1 to rules number 5. Okay, so we first identify the zero. So we don't have any zero, not available. We have the poles located at -2, -4, and -6. Okay, so if you try to locate all those poles and zero, we don't have any zero, and -2, -4, -6. Okay, that are the poles. Then we have segment here, 1, 2, 3. So we have segment at the left of odd number and the odd number here. So we have another segment. So we should understand from here, we can imagine that there will be a root locus here to the left, and there will be a root locus in between here. Okay, whether it goes to the upper side perpendicular or it goes to the right, crossing the j omega crossing point. Okay, let's identify next the asymptote point. Okay, so the asymptote point, this is rule number 5, isn't it? Rule number 5. So for the asymptote, the number of asymptote equal to the number of poles, which is 3, minus 0, which is 3. So we still have the 3 asymptotes, similar as the previous example. And the sigma A is -2, -4, -6, and -0 divided by 3. So we do have 12, 4. Okay, it is at -4. And I write it here, theta. So we have 3 theta basically because it's following the number of asymptote. So theta A1, so 0k plus 1, so 180 divided by 3. So we still get 60 degrees, similar as the previous one. Theta A2 is also we're going to have the similar degree, which is theta A3, 300 degrees. Okay, so for now, the sigma A point is exactly located at the one of the poles location, which is -4. The previous one, we have the asymptote point here, sigma A, at the different location. It's not part of the poles location, that different location. But for this one, the asymptote point is exactly also located at the same point of one of the pole, which is -4. Okay, so from here, we draw the asymptote line 60 degrees, the -60 degrees. This is 60 degrees, -60 degrees, and 180 degrees. This to the left. Okay, so the rule is still the same. in between we have a segment, then we know that we have a root locus in between, and it will break at the one point here. Okay, and it goes to the right, crossing the point at the j omega, and finally is following this asymptote line, also similar to this one, following the asymptote line. Okay, the solution is quite similar to the example number 3. Okay, as I said last week, I want to extend this class about half an hour. So let's have a quick break, about 5 minutes before we continue with the next session. we continue. So this is the second part of the root locus drawing. Just at the beginning, just now, I explained that we have two parts. One is for the sketching, and the other one is for refining. Okay, so now this is the part of refining. Yeah, we want to refine the sketch that we have done just now, from rule number 1 to rule number 5. One of the another procedure is to find the location of the breakaway and also the break-in point. Okay, so the root locus breaks away from the real axis at the point of maximum gain and breaks into the real axis where the gain is minimum. Okay. The second statement also the same thing. The breakaway point occurs at point maximum gain on the real axis between the open loop poles. Okay, let me consider this example. Okay, so if we have the location of poles and 0 like this, so we can number it 1, 2, 3, 4, and we consider the odd number. Then to the left, we have a segment and the second segment here. Okay, so in between these two poles and these two zeros, there will be a breakaway or break-in point. Okay, and basically, if it is in between two poles, the point is the breakaway point here. Okay, this is what we call a breakaway. Because the direction of the root locus should be from poles to 0. Okay, so the direction going to be like this, and it's the breakaway to another part at the left. Okay, and come to this another point here called as the break-in, and finally it ended at the 0. Right? So it ended at 0. Right. So how many branches available in this root locus? Yeah, two branches, which is following the number of poles. We have 2 poles here. Okay, so these 2 poles, it goes to the 0, another 2 0 at the left. Okay, one is goes probably like this. The animation, I think. Yeah, it goes like that. It's 2 branches, and it meet together at the break-in point, and finally it ended at the 0 here, -3 and also -4. Okay, so what does he mean by here? The root locus break away from the real axis at the point of maximum gain. Okay, the root locus, as I mentioned, it started from poles and ended at 0. Okay, at this pole, this is open loop poles, and this is finite open loop pole. So at this point, the K that we use is equal to 0. You can refer back to the example at the beginning of this chapter, where we did try on making the table by varying the value of K. So we started on when K is equal to 0, and then we added the K value, right? So it started at the K equal to 0 and ended at K equal to infinity at the 0 point, meaning that the K at the 0 point is a very huge number of K. It could be 1,000 or something that can represent the infinity value. Okay? It is not a small value, right? So at these 2 poles, at here, the k that being used is also k equal to 0, and here is k equal to 0. And when we start to increase the k, there will be a new location of poles. Okay, for example, here and here. Okay, probably this is another k. And if we increase again the k, there will be at one time the two poles are meeting at the same point here, at the breakaway point. Okay, let's say k at this breakaway point is equal to 10. Okay, and if we increase again the value of k, probably it goes to these two poles. It goes should be conjugate pair. Okay, and increase again k. Okay, let's say at this location of pole just now, this here, not here, this here, k is equal to 15. And here also k equal to 15. Right? So the statement here saying that at on the real axis, the gain is the maximum gain. The gain is maximum gain at the real axis, which is equal to k equal to 10, before it leave the real axis. Okay, when it leave the real axis, even though the gain is increasing, k equal to 15 and so on, but the maximum gain on the real axis before it break away is this gain. So this is the maximum gain on the real axis before it's leaving the real axis point. Okay, so that's what does it mean from this statement. And for the break-in point, the gain is the minimum gain. Okay, let's say up to here. Here is k equal to 50. Here also k equal to 50. Okay, and finally, when it meets at these 2 points, so it's going to be the same location. So this is k equal to probably 70. Okay, when it is increased again, here we have 2 pair of poles. So the poles probably here is equal to k equal to 100. Okay, so at the break-in point here, the k is the minimum gain, okay, on the root locus at this real axis segment. Okay, when it just come to this break-in point, this is the minimum gain. Okay, then when we increase the gain again, and the poles goes to break into 2 parts, one to the left and one to the right. Okay, but the minimum gain at this break-in point is k equal to 70. Okay, so this is what mentioned here. When the break is into, so the gain is the minimum gain on the real axis. But the other gain here is greater than this gain on this break-in point. Okay. Okay. How we can get the location, the exact location of this breakaway, break-in, and also the breakaway point here. Okay. So we can estimate that point by using the differentiation. Okay. We differentiate the forward transfer function, GHS, and then we solve for the S. So the S value here is equal to the this breakaway or break-in point. Okay, sometimes it's just on the breakaway, sometimes it's just break-in point, and sometimes it comprised of both points. Okay, breakaway and break-in point. Okay, so sigma is the breakpoint. So let we try on example number 5 here. Okay, so if let's say you are given the root locus like this, normally we are given the transfer function of the system, then we defining the poles and zero location, and we try to locate on the S-plane. But now you are given the root locus, so we have to translate it into the transfer function. Okay, so if we translate it to the transfer function, the fourth transfer function is given by K, and the zero are located at, so the zero located at +3, +5, and the poles location located at -1 and -2. So in this, from this zero information here, under transfer function, it's going to be negative this value. Okay, so we have s minus 3 and s minus 5. Okay, and we have the poles given by s plus 1 and s plus 2. It should be inverse of this value. Okay, the poles and zero value. S plus 1, because normally when we're taking what is the pole, s plus 1 equal to 0, then s is equal to -1. Back to here. But we're doing it reversely. Okay, so our transfer function is this one. Okay, let's say I have another example. The poles are located like this, and the zero is located here. And finally, the locus goes like this, goes like this, and finally ended to the 0. Okay, it's always it's typical question in the test where you are given the root locus like this. You have to first identify what is the transfer function. Okay, so you should be able to develop the transfer function first. Okay, for example here, it involves the complex number, the complex pole. Okay, let's say this is 1, this is J2, this is negative J2, this is -1, this is -2. Okay, so we have two poles and two zero. So the zero are -1 and -2. J1 and 1 minus J1. So if you put into the transfer function, so KGH is equal to K S plus 1 S plus 2 and divided by S. Okay, so from here we need make it -1 minus J1 and S minus 1 plus J1. Are you following me? Okay, so it should be like this, right? And finally, you cannot leave it like this. Okay, you have to expand this as usual, and expand it, and here time this one, and finally, this J will be will disappear from this transfer function. You only finally going to have something like this is a second order. It's something like s squared plus blah 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 without the J information, because j has been, let's say, j times j here is going to be j squared, right? Okay, j times j squared, and somehow you can try it. Okay, you can try it. If you want, you can try it together, but it takes some time. I would like to finish with this part first. Let's say we solve on this one. Okay, just now we have this transfer function. Okay, from this transfer function, okay, so we have this transfer function. Copy this one. Okay, so just now we stop here. So from here, we should expand it first. Okay, so we have s to the power of 2 minus 8s plus 15. Okay, s to the power of 2, 3s plus 2. Okay. Okay, yeah. Okay, so just now, in order to get the break-in and breakaway point, we should using the differentiation. So we differentiate d over ds of g, basically kgh. And we setting the k is equal to 1. Okay, so in that case, we are actually trying to differentiate this function. But this function, transfer function, involves x variable at both parts, numerator and denominator. So the easiest way is if we can define this as u and v, so that we can differentiate by using d over ds uv is equal to v du minus u dv divided by v squared. I hope you still remember this formula. Okay, so we proceed. So s squared plus 3s plus 2. So this is v. Du, we differentiate this one. 2s minus 8. Okay, and divided, oh, haven't finished, minus u. U is s squared 8s plus 15. And time 2s plus 3 divided by v squared. And you can write it, but finally it's going to be cancelled. Why I'm saying like that? Because everything here will be equal to 0, then we can cancel the denominator. Okay, so you need to be expand it. Okay, you expand this carefully. So we have 2s cubed and blah blah blah. Okay, and finally you will get this mathematical expression 20s minus 61 equal to 0. Okay, so from here, using your calculator, you can get the roots from here. Then you have two numbers, which is 3.82 and negative 1.45. Okay, where the s that we obtain from here is equal to the breakpoint. So either is break away point and or break in point. Okay, so don't confuse on the symbol of sigma here, because previously we also found there is another sigma, which is sigma A. Okay, the sigma is the asymptote point, but the sigma here is the break point. So this is the break point. It could be breakaway or break-in point, but this one is the asymptote point. So don't confuse. Okay. So we have two value here. One is negative, one is 3.82. So if I draw it again just now, we have 3, 5. We have 3, 5 from transfer function, 3 and 5. And we have, 3, 5 is the 0. And the left side is -1 and 2. -1 and -2. Okay, so we have, if we number it, 1, 2, 3, 4, we have a segment here, we have a segment here, we have a breakaway point from here, and it try to find the 0 at the right side. Okay, and finally it ended at the 0. Similar to this one, another branch goes to here from the downside, okay, and meet at this break-in point and finally ended at the 0. Okay, what we're trying to identify just now is the location of this breakaway point and this break-in point. Break-in point. Okay, so according to the roots that we found just now, we have -1.545, which is actually exactly located in between these 2 points. Okay, so in this case, it is -45, which is the breakaway point here. Okay, and the other value is 3.82, which is in between these two 0 value. Okay, so we have here 3.82, which is the breaking point. Okay, sometimes we have to solve for probably third order here, and we have 3 value, but from the sketch here, we only need one point. Okay, so we have to choose from the 3 possible value here. We have to match to the location of the sketching, our sketching here. For example, there's only one breakaway point here, but it involves 3 s to the power of 3. Then we have 3 number. Okay, so then from that 3 number, we choose one that is suitable to be placed in between these 2 poles. Okay, so we have to carefully select. Okay, but for this problem, it is exactly the point that we want. Okay, we have s to the power of 2, then we get 2 value, and then we can match also to the sketch that we have done here. Okay. Okay. So this is the solution. Okay, I would like to proceed with this one for the J omega crossing. So the J omega crossing, it's nothing new for you actually, because you have gone through this the route with before. Okay, when we are checking on the stability of the system in the course 3133 course last semester, we have used the road quiz criterion, RH criterion, in order to solve for the stability. But now we're trying to use again this RH criterion to get the value of j omega crossing over here. Okay. Okay, again here, we didn't give the exact transfer function. Then we can extract the information from the root locus that has been given to us. Okay, so the KGH is, we have 0, 1, 0. Yeah, we already past 1 p.m. For those who just joined this, because I already mentioned last week that we're going to extend this class about half an hour, but it's more than half an hour because we already missed 2-hour class on Monday this week. And then we're also going to miss another 1 to 3 hour class next week due to Hari Raya. And I would like to try to replace it somehow at this time. Is it okay for you? This is the last part, rule number 7. Then we dismiss. Okay, so this is the last part. It's nothing new for you. We just need to make some revision over here. So we have K S plus 3, and we have S plus 1, we have S plus 2, we have S plus 4. So this is what supposedly you can construct from the root locus that has been given here. Okay, you should be able to construct this one. Right? So from here, you can expand it. And finally, if you expand this one, you're going to have S plus 3 divided by, it's going to be S to the power of 4 because we have 4 poles over here, which is 7S3, 14S squared, S plus 8 plus K plus K. Okay, so this is supposed to be, this is still an open loop, sorry. Suppose 7S, 7S3, 14S squared plus 8S plus 8S. Okay, but when we using the RH criterion, we should get the closed loop transfer function rather than open loop transfer function. So if you're considering this is the open loop transfer function, so if closed loop transfer function, you should use kg divided by k 1 plus kgh. Then we construct from this here, we put it over here, this one to here, and we assuming that h is equal to 1 because this is the unity feedback system. And finally, we got s plus 3 8 plus k s plus k, right? So we have this value. Okay, so from here, we construct a RH table. Okay, so we have S to the power of the highest order, okay, followed by S3, followed by S2. Okay, I put some space over here to make some calculation, and finally S plus 0. Okay, so from this denominator, we plug in all those coefficients. So 1 followed by 7, okay, followed by 14, followed by 8 plus k, followed by k, and finally, so this is not k actually, this is 3k. Okay, sorry, I made mistake. So this is 3k, this is 0. Okay, alternately, we key in 1, 7, 14, 8 plus k, 3k, and finally we don't have any more number, then we just put 0. Then we fill in this one, which, okay, the next blank value here. So we multiply like this, 7 times 14, we got 98 minus 8 minus k, k divided by 7, right? And we have 90 minus k divided by 7. And this one, 7 times 3k, we have 21k minus 1 minus 0 divided by 7. Okay, you have to review again this part if you don't understand. Okay, or understand. Okay, then we have 0 here because 7 times we don't have any more number at the right side here, 0, 0, and we have 0. Okay, so to simplify further, you can just subtract this one, cancel this one because it has the same denominator. So remain is 90 minus k and 21k. Okay, so we follow to the next part, next row. This one times this one, so 90 minus k, 8 plus k, and minus 7 times 21k. Okay, so we have 147k and divided by the same number here, 90 plus k and 90 minus k. And finally, if you simplify this one, you can subtract the denominator, just considering the upper part, the numerator part only. And finally, we got k squared plus 65k minus 720. And this one going to be 0 because this one, we time this one, minus this one times this one. So we got 0 and 0 and so on. And the following row, this one times this one, it is the 21k, and divided by this one. So we remain this one as 21k. Okay, so from this table, we know that the 0, row of 0 should happen over here at the odd number. Okay, so this is the row of 0. Right? So everything at this row of 0 should equal to 0 plus 65k minus 720 is equal to 0. Then we can solve for k value. So k is equal to 9.65 by using your calculator and 74.65. Okay? But this is not possible because the k value, the gain, should be a positive gain because in the root log the k is started from a 0 to infinity. Okay, so this is not possible. Okay, we can cancel this one. Then we choose this one as the value of k. Right. So in terms of the stability, the system will stable at this region. So you have done actually this one in previous course. It should be from 0 to 9.65. So this is the stability range. And the system is not going to be stable when k is greater than 9.65. Right? So this is just a revision. But we extended it to by looking at the previous row, and then we construct the auxiliary equation. So PS is equal to 90 minus K and S squared, because this is belong to S squared, plus 21K S0. Okay. Substitute now the value of K here that we obtained just now, and K over here we also obtain 9.65. Okay. So if we substitute, then we have 80.35 squared plus 202.65 equals 0. Okay. So x squared is equal to negative 2.52. So s, because this is square root of negative value, so we're going to convert it into plus minus j and the number of the square root, which is 1.59. Okay, so basically the value here plus minus 1.59 is actually the value of the one. Yeah, it's the value of j omega crossing value over here. We call it as j omega crossing point. Okay, we got just now j 1.59 and here is negative j 1.59. So from the root R hash table just now, we extended it to looking at the previous row to construct what we call as the auxiliary equation. The auxiliary equation, we make it equal to 0, then we solve for those values. So, okay, this auxiliary equation, we solve for the S. Okay, so the S that we obtain is actually the j omega crossing point at the root locus, for the root locus. Okay, so the solution also here, you can refer it back, can make a practice from this one. Okay, where make sure that you be able to solve this RH table here. Okay, and how you constructing this, putting all this coefficient from the transfer function, how you fill in this table, you should master on it. You have done it before, then you need to use it again now. Right? So I think that's it for today. So we dismiss the class up to here. Okay, is there any questions so far? So we already covered up to rule number 8. We just remaining another rule, which is rule number 9. Okay. Okay, we have another 2 rule actually. Departure angle and arrival angle, and also the gain adjustment. Okay, we have covered up to rule number 7. Any question? Okay, so far so good. Okay, as usual, I will share this video in the e-learning once it is ready, because normally WebEx takes some time to construct to compile the video. Okay, it takes 2 to 3 hours after this meeting. All right, that's it for today. Thank you very much, and happy Hari Raya for the Muslim, and also happy holiday for the rest. And that's it. Thank you very much. Okay, see you again. So I'm not so sure whether next week you're going to have a class or not. It seems that it's difficult to make it. Thing that I probably can do is probably I'm doing the recorded lecture. Are we going to just meet this continue the class after the Hari Raya? Okay. Selamat Hari Raya. Assalamualaikum warahmatullahi wabarakatuh. Okay, see you again. Assalamualaikum.
Wassalam. Thank